Yes, when your service is a 480-volt delta system, it is generally required that one of the phases be bonded to ground. This practice is crucial for several reasons, primarily related to safety and the proper functioning of overcurrent protection devices. In a 480-volt delta system without the grounded phase, the voltage to ground on each of the three phases is not fixed. This can lead to voltage imbalances and potentially dangerous conditions. Grounding one phase establishes a reference point, ensuring that the voltage from each ungrounded phase to ground does not exceed a predetermined level. This is vital for protecting equipment and personnel from insulation breakdown and electrical shock hazards. Firstly, grounding a 480-volt delta system provides a path for fault current to flow back to the source. When a fault occurs, such as a phase conductor coming into contact with a grounded enclosure, the resulting fault current will follow the path of least resistance back to the source, which is typically the transformer. This high fault current will then activate overcurrent protection devices such as circuit breakers or fuses, causing them to trip and energize the circuit. Without a grounded phase, the fault current may not be high enough to trip these devices, leaving the fault unaddressed and posing a significant safety risk. The presence of a ground fault path ensures that these protective devices function as intended, quickly clearing the fault and preventing further damage or injury. Secondly, grounding one phase in a 480-volt delta system helps to stabilize the voltage to ground. In an ungrounded system, the voltage to ground on each phase can fluctuate, especially if there are imbalances in the load or if the system is subjected to transient voltage surges. These voltage fluctuations can stress the insulation of electrical equipment and can lead to premature failure. By grounding one phase, the voltage to ground is fixed, preventing these fluctuations and providing a more stable and reliable electrical system. This stability is essential for ensuring the proper operation and longevity of electrical equipment connected to the system. The grounded phase serves as a reference point, mitigating the effects of voltage imbalances and transient surges, and maintaining a consistent voltage level to ground. Thirdly, grounding a 480-volt delta system facilitates the use of line-to-neutral loads. While a delta system does not inherently have a neutral conductor in the same way as a Y system, grounding one phase allows for the creation of a derived neutral point. This derived neutral can then be used to supply single-phase, line-to-neutral loads, such as lighting or small appliances. This is particularly useful in industrial or commercial settings where both three-phase and single-phase loads are required. Without grounding a phase, it would be difficult or impossible to supply these single-phase loads directly from the 480-volt delta system, necessitating the use of additional transformers or other voltage conversion equipment. By grounding one phase, the system becomes more versatile and adaptable to a wider range of electrical needs. Furthermore, the National Electrical Code, often abbreviated as NEC, provides specific requirements for grounding 480-volt delta systems. The NEC mandates that electrical systems be grounded in a manner that ensures the safety of personnel and equipment. For a 480-volt delta system, the NEC typically requires that one phase be grounded unless certain specific conditions are met. These conditions usually involve the use of ground fault detection systems that can detect and isolate ground faults without relying on a grounded phase. However, in most cases, grounding one phase is the simplest and most reliable way to comply with the NEC requirements and ensure the safe operation of the electrical system. It's essential to consult the latest version of the NEC and any applicable local codes to determine the specific grounding requirements for a given installation. Moreover, it's important to understand the different types of 480-volt delta systems and how the grounding requirements may vary. There are two main types of 480-volt delta systems: firstly, the corner-grounded delta, and secondly, the high-leg delta. In a corner-grounded delta system, one of the phase conductors is directly connected to ground. This is a relatively simple and straightforward grounding method, but it can have some drawbacks. For example, it means that two of the phase conductors will have a voltage to ground of 480 volts, while the grounded phase will have a voltage to ground of 0 volts. This can create some confusion and can make it more difficult to troubleshoot ground faults. In a high-leg delta system, a center tap on one of the transformer windings is grounded. This creates a high leg or wild leg that has a voltage to ground of approximately 208 volts, while the other two phases have a voltage to ground of 240 volts. This system is commonly used when both three-phase and single-phase loads are required, but it's important to be aware of the high leg and to properly identify it to avoid accidentally connecting single-phase loads to it. In addition to grounding one phase, it's also important to properly bond all non-current carrying metal parts of the electrical system together into the grounding electrode system. Bonding creates a low impedance path for fault current to flow back to the source, ensuring that overcurrent protection devices will trip quickly in the event of a fault. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes that are connected to the building's grounding system. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage to ground and to dissipate any stray currents. Proper bonding and grounding are essential for ensuring the safety and reliability of the electrical system. To elaborate on the corner grounded delta system, it's crucial to understand its specific characteristics and applications. In this configuration, one of the three-phase conductors is intentionally connected to ground, effectively making it the grounded conductor. This approach simplifies ground fault detection, as any fault to ground on the other two phases will result in a high fault current that will quickly trip the overcurrent protection devices. However, it also means that the voltage between the two ungrounded phases and ground is equal to the full phase-to-phase voltage of 480 volts. This can be a safety concern, as it increases the risk of electric shock if someone comes into contact with an ungrounded phase and ground simultaneously. Therefore, corner grounded delta systems are typically used in applications where simplicity and ease of ground fault detection are paramount, such as in some industrial settings. However, they are less common than other grounding configurations due to the higher voltage to ground and the ungrounded phases. Expanding on the high leg delta system, it's important to understand the origin and implications of the high leg, also known as the wild leg or stinger leg. This configuration is derived from a delta-connected transformer with a center tap on one of the windings. The center tap is grounded, creating two voltage levels. Firstly, a lower voltage of 240 volts between each of the two phases not associated with the center tap and ground, and secondly, a higher voltage of approximately 208 volts between the high leg and ground. The high leg is 1.732, the square root of 3 times 120 volts, which equals to 207.84 volts, is typically marked with orange or another distinct color to indicate its high voltage to ground. This is crucial because connecting a 120 volt load to the high leg will result in damage to the equipment due to the overvoltage. High leg delta systems are often used in older installations or in situations where both three-phase power and single-phase 120 volts power are required, such as in some light industrial or commercial buildings. However, they are becoming less common due to the complexity of managing the high leg and the potential for misconnections. Furthermore, it is essential to understand the role of the equipment grounding conductor, abbreviated as EGC, in a 480 volt delta system. The EGC is a conductive path that connects all non-current carrying metal parts of the electrical system, such as enclosures, conduit, and equipment frames, back to the grounding electrode system at the service entrance. The purpose of the EGC is to provide a low impedance path for fault current to flow back to the source, ensuring that overcurrent protection devices will trip quickly in the event of a ground fault. The EGC is typically a green or bare copper conductor and is sized according to the requirements of the NEC, based on the size of the overcurrent protection device protecting the circuit. Proper installation and maintenance of the EGC are critical for ensuring the safety of the electrical system. In addition to the equipment grounding conductor, it is also important to understand the role of the bonding jumper in a 480 volt delta system. The bonding jumper is a conductor that connects the grounded conductor, if present, to the equipment grounding conductor at the service entrance. The purpose of the bonding jumper is to ensure that all non-current carrying metal parts of the electrical system are effectively bonded together and to the grounding electrode system. The bonding jumper is sized according to the requirements of the NEC and is typically a copper or aluminum conductor. Proper installation and maintenance of the bonding jumper are critical for ensuring the safety of the electrical system. Moreover, the size of the grounding electrode conductor is crucial for proper grounding and safety. The grounding electrode conductor connects the grounding electrode system to the grounded conductor or the equipment grounding conductor at the service entrance. The size of the grounding electrode conductor is determined by the size of the service entrance conductors as specified in the NEC. A properly sized grounding electrode conductor ensures that the grounding electrode system can effectively dissipate fault current and maintain a stable voltage to ground. It's essential to consult the NEC tables to determine the correct size of the grounding electrode conductor for a given installation. Furthermore, understanding ground fault protection is paramount for ensuring safety in 480-volt delta systems. Ground fault protection is designed to detect and interrupt ground faults, which are unintentional electrical connections between a phase conductor and ground. Ground fault protection is typically required for large electrical services, as specified in the NEC. Ground fault protection devices, such as ground fault circuit interrupters abbreviated as GFCIs and ground fault relays, monitor the current balance between the phase conductors and the neutral conductor if present. If an imbalance is detected, indicating a ground fault, the device will trip and de-energize the circuit. Ground fault protection can significantly reduce the risk of electrical shock and fire in the event of a ground fault. Furthermore, it is important to consider the impact of harmonics on grounding in 480-volt delta systems. Harmonics are non-sinusoidal currents and voltages that can be generated by electronic devices such as computers, variable frequency drives, and lighting ballasts. Harmonics can cause a variety of problems in electrical systems, including overheating of conductors and transformers, increased neutral currents, and voltage distortion. In 480-volt delta systems, harmonics can exacerbate existing grounding issues and can lead to nuisance tripping of overcurrent protection devices. To mitigate the effects of harmonics, it may be necessary to install harmonic filters or to use oversized conductors and transformers. Considering surge protection in 480-volt delta systems is also crucial. Surge protection devices, also known as transient voltage surge suppressors abbreviated as TVSSs, are designed to protect electrical equipment from voltage surges caused by lightning strikes, switching operations, or other transient events. Surge protection devices divert the surge current to ground, preventing it from damaging sensitive electronic equipment. Surge protection is particularly important in areas that are prone to lightning strikes or where there is a high concentration of electronic equipment. Surge protection devices should be installed at the service entrance and at sensitive loads throughout the electrical system. In conclusion, grounding a 480-volt delta system is generally required to provide a safe and reliable electrical system. Grounding one phase provides a path for fault current to flow, stabilizes the voltage to ground, and allows for the use of line to neutral loads. The NEC provides specific requirements for grounding 480-volt delta systems, and it's essential to consult the latest version of the NEC and any applicable local codes to ensure compliance. Proper bonding and grounding are critical for ensuring the safety of personnel and equipment. It is crucial to understand the different types of 480-volt delta systems, the role of the equipment grounding conductor and bonding jumper, the size of the grounding electrode conductor, ground fault protection, the impact of harmonics, and surge protection to ensure a safe and reliable electrical system. Always consult with a qualified electrician or electrical engineer for specific guidance on grounding requirements for a particular installation.